A very warm welcome. Good morning, good afternoon, good evening, depending on what time zone you are. A very, very warm welcome to this wonderful webinar organised by the Simsine Library. Today, for the next hour, you're going to hear from some amazing speakers who are going to be talking about the teaching and learning physiology using model-driven patient simulators. So let me introduce the speakers to you. We have some keynote speakers who are world-class in their fields. We have Richard Helyer from the University of Bristol, Eugene Lloyd from the University of Bristol, Kat Harrison from the University of Bristol, and Willem van Meurs, who's a consultant in simulation. And my name is Amanda Wilford. During this webinar, please can you put any questions into the box, and at the end we will ask the panel some questions, so please keep writing all the way through. This meeting is also being recorded. So without further ado, I'd like to ask Eugene, who's going to start us off. So Eugene, over to you.
Thank you, Mandy. So Stefan Monk put this paper together that has shown the challenge that we face worldwide with it's estimated that we need an extra 10 million additional healthcare workers in order to provide adequate care by the year 2030. And at the same time, we're faced with the other major challenge in healthcare, which is medical error and damage done by the practice of medicine. And it's said that approximately 2.6 million deaths per year are due to unsafe medical care. I think it's important to realize that some of those deaths will be unavoidable, and we'll never, I don't think we'll ever achieve zero deaths, but our aim should always be to reduce those deaths and make healthcare safer. But Stefan points out that two of the major problems that we face here, and these are not new problems. Number one is that we don't have enough educators and we don't have enough clinical placements. And having been involved in reviewing and developing a new medical degree for Bristol, these were two of the things that we really had to contend with, was number of educators and number of clinical placements. And in the UK, there's certainly a drive to increase the number of medical students, of doctors that we train. And there are some new medical schools that have just come online this year. And I think clinical placements and educators are going to be an ongoing issue for future healthcare challenge. Next slide, please. So simulation offers part of the answer to these problems. Traditionally, before we had current generation of simulators, training of nurses and medical students involved the use of patients, of lifeless dummies, of students learning on each other, of learning via animal experiments. And those situations become much more difficult for various reasons, especially the use of animals. And it's thought that simulation could reduce the amount of errors in terms of healthcare by about 26%. So potentially saving 1 in 4 lives. So that when you think about globally, that potential reward is huge. But also it reduces the time taken to achieve competence in terms of particular skills. And this is another area where simulation Okay, so my background initially was training in medicine, and I have to admit that I never even bought myself a textbook of physiology. as a student. And I think one of the problems we've always faced is if you talk to a member of the public, to a lay audience, essentially everybody has an idea of what anatomy is, as in different parts of the body. But physiology is the subject that isn't really out there in terms of what it means. And my way of one of the descriptions I've heard of it is that if you think of anatomy as a stage, then physiology is a play that goes on, or a performance on that stage, which I quite like. I'm sure the anatomists wouldn't like that, but I like that description. So it's derived from the meaning of the study or the logic of life and living processes. And so very much it's an experimental subject. I don't think you can have a completely theoretical approach to learning physiology. It has to be through experiment. And recently these pictures from the archives were discovered, and they're from essentially late 19th century, early 20th century at Bristol. And the first picture you can see there is the professor of physiology at the time demonstrating some analysis. And reading the small print, what he was actually demonstrating was some blood gas analysis. So very different compared to modern blood gas analyzers and the data that we get from our simulator. So it's definitely developed. And then the other picture shows a lecture hall. And you can see there that there's a professor at the front of the lecture. He's got three assistant technicians, or three faculty with him. And there's a number of people in the audience. And I did a rough head count, and it's approximately 30 people in the audience. And when I looked at the ratio of staff to students, the ratio is about 0.13. And Rich will pick up on that later in the slides. I think it's quite fascinating, that particular ratio, as Rich will explain. But I think the other thing to notice is that if you look at the audience, from what I can see, they are all male. They are all of Caucasian background. And I suspect that they were all from a relatively affluent background within society. So the audience has certainly changed. It's not only got larger, so this class was 30. Our current classes are approaching 300, and there's much more diversity within the classes. So some of our students come straight to university from having studied their A-levels, others come from the world of work, others have done other degrees. So there's much more variety and variability in the students. Next slide, please, Amanda. So it would no longer be feasible to perform animal experiments for medical students, and for safety and ethical reasons, we can't bring in patients, especially patients that are unstable. So these two photos show what we're doing now. So we have a virtual patient. And again, the importance there is that we can simulate patients from different ethnic backgrounds, which is really important to ensure that all our audience appreciate the importance of biological variability and diversity. And during the pandemic, there was a paper published that showed that measurement of oxygen saturation using a pulse oximeter could be very different depending upon skin tone and skin color, and that is obviously very relevant. And then in terms of the photograph, you can see that the audience is now much larger. So as I say, this is a lecture theatre with approximately just under 300 people, and from multiple backgrounds. And at one point, we actually changed from a ratio of 100% men to 70% female. Now it's almost 50-50, which is probably the way it should be. So I think the other thing in terms of patient safety, it's about having our students learn from very early in their course about the importance of measurements and the numbers, and the information that they get from a clinical monitor. And we found that it's very helpful to be able to project that information so that the entire lecture theatre can see it and understand what we're talking about and referring to. Next slide, please. So this is a timeline of the work that Rich and I and others have been doing since about 2005. And in 2005, we were fortunate to have quite a large amount of money available to us that allowed us to develop the use of simulation, in particular for biomedical education. So obviously, as you all know, that its use in clinical education has been going on for much longer, but we wanted to use the technology for biomedical education for medical students, also dentists, vets, BSc students, etc. And we purchased 2 METI simulators, and we built 2 simulation suites. And that actually constrained us a little because there were certain limits on the number of students we could get into a simulation suite, the number of staff that were required. But at the same time, it did mean that the students were able to interact with a physical mannequin. And Rich will talk a little bit later about how this has developed over the years, how the technology's changed, how our approach has changed, and how things like the COVID pandemic have impacted upon the learning experience, but not in necessarily a detrimental way, as Rich will show. Okay, next slide, please.
Okay, I'll take it over from here, Eugene. Did I recognize you in that historical picture? Simulation is all about, or physiology is all about systems. And we talk about the cardiovascular system, about the immune system. And my purpose here is to talk about the systems behind the information that Eugene talked about, the information behind the clinical signs and behind the monitored signals. And my purpose in a few slides is to lift some of the mystery behind the models that we use in model-driven simulators. So when I look at a patient or a simulator, I observe clinical signs like cyanosis and monitored signals like invasive blood pressures. And if these variables, these quantities can change spontaneously, and if they go in the out of range for what we consider normal for a patient, we have to do something to this patient. And that's when we apply therapeutic interventions, for example, connecting a ventilator or administering fluid. So I look at the patient as a system where therapeutic interventions influence clinical signs and monitored signals. And those relationships depend on the state of the patient, for example, hypoxia, hypercarbia, and they depend on certain patient characteristics, like what is the baseline shunt fraction or systemic vascular resistance of this patient. Now, to go one step further in with our simulation engine, I'll open the hood for you. And that's the second diagram, the more complicated diagram on this slide. But allow me to tell you first why we're doing all of this. So I've given you the presentation of the patient. Now, in a simulator, we would like these clinical signs and monitored signals to change automatically without intervention by an instructor or technician. And that's why we rebuilt this box, we rebuilt this patient. And so what you see on the right side is the different subsystems, we engineers call them, that we build into these model-driven simulators. On the left side of the bigger diagram, we have ventilation and circulation, which is where we compute volumes and pressures and flow rates of blood and of gases. And those then go into a transport and metabolism system. And you may remember from your physiology classes, the ventilation perfusion ratio, VQ and a VQ mismatch, that all happens at the transport and metabolism level. When oxygen and CO2 and drugs get to mostly to the brain, but sometimes to other effect sites, they start influencing both breathing and circulation. And for example, when a patient gets hypoxic, the ventilatory drive will increase, what we call ventilatory control effectors, and breathing will become deeper and faster. And also when there is hypoxia, the heart rate will go slightly up. Heart rate not only depends on blood gases, it also depends on arterial blood pressure. And if there's a low blood pressure, heart rate will go up and contractility will go up, and a couple of other circulatory control effectors will change. Now, what I'll do next is that I'll do the same thing as going from the first to the second diagram. I'll open up two of these boxes, and we're going to look a bit more in depth at ventilation and circulation. Next slide, please. So what you see on the left, and I will not treat the whole diagram on the right, which is on the cover of our book, but on the left, there's the diagram or the conceptual model of how lung and chest wall mechanics are represented in our simulators. And I use two kinds of symbols in that diagram. The opposing triangles are resistances, and the circles are what we call capacitances or elastic structures. They're essentially a representation of the pressure volume relationship. So air goes in from the mouth, which starts at where ventilation pressure is indicated, flows through a dead space and through left and right resistances, which are mainly bronchial resistances, usually the same left and right, but they can, of course, be increased for one side or the other. And air gets into the lungs and the left and right alveolar spaces. The lungs themselves are suspended in the thorax, and we split the chest wall in left and right chest wall, and that's why we also divided the chest wall, or the chest wall compliance, by two there. And what causes breathing, other than an outside pressure, are the respiratory muscles, and the respiratory muscles pull on the chest wall, which then reduces intrapleural pressure, the pressure around the lungs, which opens up the lungs and pulls in air. Now, what we do then to create these simulators is we translate these symbols into equations. And that's and these equations are translated into code. That sounds very technical, but it's actually the easiest part of my work. What we've seen now is how to represent physiology in a diagram is usually the harder part of what's behind the simulators. The diagram on the left is described in detail in the book, but it represents the circulation, and you can see, for example, at 1:30, 2 o'clock, you see the left atrium, the left ventricle, there are valves in between, and flow is being created and goes around the circulation. I won't go into more detail about that. The next slide, please. So once we translate these diagrams into equations and then into code, we can drive the information that Eugene talked about. So we drive, for example, The blood pressures on the monitor emulator, you can see an arterial blood pressure, a pulmonary artery blood pressure, and a central venous pressure. And we also drive clinical signs. For example, on the virtual patient on the right, there seems to be some cyanosis, which also comes straight out of these models of human physiology. So this gets us back to the monitors and the patient that we use in our simulation. Next slide, please.
So when we were writing the book, we thought about the way that we'd designed scenarios as we use them with our undergraduate students at Bristol. And it's based upon the hypothetico-deductive learning. And I'm not going to go through each in detail, but I'll make a couple of observations. And I think one of the first things is that when students look at traditional textbooks and they see various graphs, they never really pay that much attention to them. They never actually think, what is the graph actually telling me? And so part of what we're doing is actually, and it was one of our early students that described this, was that we're bringing physiology to life, that they are actually looking at interventions, plotting graphs, coming up with hypotheses, testing them, analyzing, etc. And I think there are a couple of things that this also brings out that in general are important in terms of patient safety. And that's looking at serial measurements, that actually often when you look at pulse rate and blood pressure, it's the trends rather than absolute numbers that are important, because the trends can tell you whether things are stable or perhaps whether a patient is responding to treatment and improving, or whether they're actually deteriorating. Though sometimes the absolute numbers are important. I remember a junior doctor called me up one day and wanted to discuss a patient with me. And they said, oh, blood pressure's a little bit low, etc. And I felt a little bit uncomfortable at this conversation. So I actually went to see the patient for myself, and the patient's blood pressure was extremely low. In fact, it wasn't recordable, and neither did they have a pulse. So actually, absolute measurements sometimes are important. And I think, philosophically, I think physiologists and scientists ask the question, how? And how does this work? How is this important? And physicians often ask why. So given a set of observations, given clinical signs and history, what is the unifying explanation? And part of what we do, sometimes we're using virtual subjects. So we're taking a healthy human subject and subjecting them to levels of stress that we couldn't do with a human subject. So, for example, by taking out increase in volumes of blood to look at how things change. And sometimes we're using virtual patients. So, for example, in terms of arterial blood gas analysis. And I think the other thing that we've never actually looked at in detail in terms of research, but we probably should, is whether students that have been through this methodology have a better understanding of the actual numbers involved. So, for example, a change in arterial pH from, say, 7.4 to 7.2 may not appear that great to students in terms of not a large change, but actually can be quite significant in clinical practice. So this slide really is looking at the stages involved in our simulation, and we talk about this much more in the book. But as I said, it's based upon the hypothetico-deductive model, and in particular, the use of model-driven simulators is very useful in this, because it means that the instructor doesn't have to worry about things such as heart rate and cardiac output and mean arterial pressure changing appropriately, because the modeling, as Willem has just described, does that for us. We know that that's going to work. And that means that you can use the same simulation, if necessary, on different audiences, and you will almost always get the same results. Whereas if you use an animal experiment or use patients, you have biological variability that you can't always predict. Okay, next slide, please. So this is another scenario that we use. So the pathophysiology of diabetic ketoacidosis. And we use this for our medical students, we use it for BSc students, etc. And the underlying processes are slightly different in terms of what's going on. So, for example, for our medical students, we don't tell them that this is a patient with diabetic ketoacidosis. We tell them this is a patient who is known to be diabetic and is producing large quantities of urine and is becoming progressively more unwell. And then in terms of further data, they find out that the patient has glycosuria, and they confirm this on the basis of we simulate dipping some urine to detect the high levels of glucose, and we provide them with urine electrolyte results that point out that the patient also has hypokalemia. And also we use this to link with other cases that the student has seen either via simulation or in their small group case-based learning, because I think linking between cases and pathophysiology is really, really important for developing a sort of cohesive understanding of the subject and building upon it. And also there's the opportunity to link with aspects such as membrane potentials, etc., that were traditionally taught relatively early on within physiology curricula for medical students, when they actually don't actually see the relevance of it. So actually teaching these concepts a little bit later make the concepts much more powerful. And also, the simulation shows that one of the effects of insulin treatment is that it can actually cause hypokalemia. So when the students are suggesting what treatments are required, as Kat will show a little bit later, they appreciate that potassium supplementation can become quite important in these patients. Otherwise, it can have quite dramatic effects. Next slide, please. So this is a graph of Ernst Starling. So Starling was a physician and physiologist at University College London. And the picture shows him with his experimental setup was looking at a heart-lung preparation in dogs. And it was him and several others who were the first to work out the relationship between central venous pressure or preload and stroke volume, or the amount of blood ejected by the heart per beat and also per minute. So this is a really important relationship and has effects. Even simply standing up will alter this relationship a little. And we get our students to look at these effects by increasing the amount of volume of blood that's being removed and looking at the effects on both central venous pressure and stroke volume. And one of the things that you can see there on the x-axis are central venous pressure in millimeters of mercury, and they see that there's a negative pressure. And this in itself is an opportunity for discussion, and that discussion being that many of the pressures that we measure in the human body are relative to atmospheric pressure. So they're not relative to zero pressure, it's relative to atmospheric. So a pressure of -1 millimeters of mercury means that it's slightly below atmospheric pressure. One of the things that are really important in terms of undergraduate education is face validity. So they have to understand that what they're learning has relevance to their future practice. But also we have to ensure that it's included in their assessment. So we have to ensure that there are questions on their exam papers that test the learning that we've illustrated using the simulator. And there are some examples there of the different types of question that we use. And we now use a methodology called progress testing, so that the students are sampled on a broad range of questions right from the start of the course up until when they do finals. So that means that there will always be questions on physiology and applied physiology in terms of simulation whenever they do a written exam paper covering the entire course. Next slide, please, Mandy.
So when we made the move from small teaching groups to large whole cohort groups, we knew that we had to change the way that we deliver the information during a session. So as we all know, learning is not a spectator sport, and we soon realized that making our sessions interactive was a great method to increase student engagement and encourage active learning. So at Bristol, we use some software called Mentimeter to deliver our presentations, as this program is really all about utilizing interactivity through polling, quizzes, Q&As, and word clouds. So students are able to simply scan a QR code on their phone or join from their laptops and participate in any of the interactive slides in the presentation. So it's all completely anonymous, which gives the students confidence to answer the questions without fear of getting it wrong. We've put together a couple of examples of past slides that we've used. So on the left is what we call a pin on the graph. This particular form of interactive slide is really perfect for a session that we call acid-base disturbances, where we use a nomogram to determine which disorder the patient is suffering with. And on the right-hand side is what we find to be the most powerful tool called word cloud. And students are able to type in their answer to the question, and the words will get bigger or smaller depending on how many other students have submitted the same answer. Our sessions have really become quite dynamic, and we are able to get a clear idea on the subject matter that the students are understanding with confidence, as well as areas that they seem to be struggling with or are completely in the wrong ballpark. We also use Mentimeter to gain feedback from students at the end of the session. So we can ask questions such as, did this simulation aid your understanding in the subject? And then we can then present this feedback to the head of our school or the head of our department and basically say, look, simulation is really essential for our teaching. We need to keep these sessions. Maybe we need more sessions. And really, how can they dispute its importance when we have hard data in our hands that says students are not only enjoying our sessions, but they're also benefiting from them as well. Next slide, please.
Kat. So I'm just, before I move on to one of the kind of the nub of some of what we're doing, just one more thing about data. And the key thing for us really teaching physiology is the data and the clinical signs that the simulation provides. I'm a physiologist, whereas Eugene is a clinician as well. So we have slightly different emphasis, as Eugene explained in the slide with the scientist and the doctor. Our scenarios can be written in a set way. One scenario can go in quite different directions. One slightly different direction that our scenarios go in, and we use our simulation rather, is in senior projects. And these are projects that are carried out usually in the final year of a bachelor's degree, sometimes by medical students or other students like vets or dentists who are joining us for a year. Over the years, we've gone from probably in our final year of physiology class, maybe to 30 students who would be placed in research laboratories to gain practical skills in the physiology lab, to something like about 180. And we can't accommodate those students in a meaningful research experience. And the pressures on labs are so much greater. We found that simulation can provide, we think, very deep learning opportunities for our students to have a fully experimental experience when they're carrying out these extended projects. And these projects go on for a number of weeks, something like 12 weeks in a term. And what we've done with our students is we ask them to explore maybe a challenge to physiology or some pathophysiology, sometimes of their choice, which provides challenges. We all have to learn about something, maybe fetal physiology or something like this that we don't know much about. And they explore in considerable detail. They go into the literature, they find out what should be happening, and then they challenge the simulator and challenge the model in all kinds of ways that probably Willem won't have thought students would be probing the model. And they can produce data. And you can see on the slide on the right, just if we look on the graph, it's rather small, but that's data students collected for acclimatized and unacclimatized individuals exposed to hypoxia, so at altitude, and compared to how the simulator responds. And then using these kind of data that the student are producing and results, we can go on to design scenarios. So it has a real worth for us. And we think our students really enjoy these projects, and they're valued equally to laboratory projects now in Bristol. And there's more in our book about how these operate. Can I have the next slide, please? Now, the one thing that over the years at meetings people have always asked me is, how are you going to get 300 students, maybe through multiple simulation classes on multiple subjects in one honours bachelor's programme? As an example, I run a unit called Fundamentals of Bodily Function for biomedical sciences students, first years. And they do 6 simulations as part of their class. And there's 180 of those students. Now, to put those students through a typical simulation suite environment with mannequin, facilitator, and technician would require multiple repeats of the same session. We used to put our medical students through a small suite environment. It required about 8 repeat sessions over 2 days, usually with multiple faculty and with at least 2 technicians. And that scale is unsustainable. And the question is it required for teaching physiology? And our answer is no, because unlike many simulation centres, our students learning physiology do not have to really do too much in the way of practical skills. Most of the time, they're looking at the data produced and are deciding what to do with those data, what is happening, the how, the why, and deducing what might be happening with physiological mechanisms. And for early years medical students or healthcare students, vets, dentists, and we don't have nurses, but we could have in Bristol, we think that's equally important. The why, as opposed to the why, the how, the deduction, as opposed to the doing. So what this allowed us to do, the next slide please, is upscale and take simulation outside of the simulation suite. And in the picture on the left, you can see, hopefully we've moved, well, there is a little mobile tetherless simulator there, just poking the head up, that's CA Athena. And there's Kat and a member of faculty, and that room will accommodate 140 learners. And they're all in front of computers, so they can download worksheets and fill in what's going on. Looking at signs, simulated clinical monitoring, or an image of the mannequin, for which we use cameras, projected onto big screens. So they're looking at a simulation, a physiological process or pathophysiology unfolding in real time. That really helps us scale up. We're then talking about maybe for 280 or 300 medical students, pretty much just 2 sessions. And that means they get me or Eugene or another member of faculty fresh. They get someone that is used to teaching in simulation in each session, and they get Kat as our specialist technician. We've now, with the advent of virtual patients, really kind of closed a loop that I'm going to talk about with my last slide in a bit. And this is a picture of me teaching in a class of 280 medical students, the whole class in one go. And that whole class seeing the virtual patient and monitored signals and quantities appearing and changing in real time as we progress through a scenario. It's not just me telling a story and the students watching what's happening. Kat has already shown you how we engage the students, questioning, asking via Mentimeter, word clouds, what the biggest problem they're seeing is. What should we do next? Should we give insulin? We'll give insulin and we'll see the patient deteriorate. We should have given insulin and potassium. So then we watch that happen. All of this is a very interactive process. It isn't just didactic. And you can see those students, well, you won't be able to see probably, but they've got their worksheets open. I can tell because I'm used to looking at it. And 99% of them are engaged, actively watching what's going on or discussing with their partners adjacent what might be going on to fill in the worksheets. They're not just surfing the web. Can I have the next slide, please? So Eugene has already introduced you to this timeline. And this timeline is from our initial learning when we have about 15 students packed into a suite. So we started off with higher numbers than probably most people are used to in a simulation suite. And we call this the FL ratio, the faculty to learner ratio. And initially that was about 0.13, 2 faculty with 15 students. Imagine getting through a class of 300. And as we upscale to medium-sized groups, then to larger groups, and then to tetherless mannequins in 2016, around then, you can see our ratios really get smaller and smaller. 2016, we're going to a ratio of 2 faculty with 84 students. And that's just because that's how many fitted into a particular rotation. The students are off doing other things when we're not teaching them a sim. Satisfaction scores, and unfortunately, due to this going on for about 20 years nearly now, lots of things changed in measuring student satisfaction. You know, we didn't unfortunately look at this as a methodical process over 20 years. It'd be wonderful if we had. But scores for student satisfaction were unchanged. They were always good, and they were always as good as other types of practical class, experiential practical classes. And the test scores that students were getting were unchanged. As we upscaled, there was no difference in satisfaction, no difference in test scores. We got some peculiar things as well, like students telling us they preferred to be in a large lab because they didn't feel confined in with the simulator and a over-enthusiastic instructor. So it's very, very interesting what came out. COVID meant we had to move everything online. And one of the things we're really proud of achieving in Bristol is not losing a single session that involved simulation. We simply moved them online. We dispensed with the mannequin. Remember, for me, physiology, how much do we need a mannequin? That's a good question. I'd say not too much. And so we went to just showing signs and signals. So we showed then that we could teach for the faculty to learner ratio, and it was about 2 to 251, but it could be as many people as you could get online. Again, no change in test scores or satisfaction. Things really came round in terms of interactivity, I guess, in some ways, is what I'm going to finish on in a second. And we went to virtual patients. And you may think it doesn't look very interactive, but Kat's already explained one way that it is now, and some hope for the future as well. But then we went to virtual patients, and we're going back to a ratio in 2022 of about 2 to 120, so about 0.02. Now we're up to 2 to full classes of getting up to 300 students, all getting one session. So one uniform session with an experienced member of faculty, and a very experienced specialist technician. So this is how we've really upscaled things, but while maintaining learner satisfaction. So reducing the FL ratio, maintaining learner satisfaction. Can we have the next slide, please? The final thing I really want to say about virtual patients is, for me as a physiologist, this is the most exciting development. It's exciting for several reasons. One reason, as I've kind of alluded to, is that we can embed simulation-based learning in pretty much any program now. If I encourage people, or my colleagues want to run a simulation, maybe about the endocrine system or about homeostasis, descent to altitude, alcohol tolerance, whatever, it can be quite hard to embed these simulations into the curriculum if you've got to find 2 full days, several members of enthusiastic staff, and cat's time for 2 days. Virtual patients allows me to, if you like, be able to pretty much embed a simulation anywhere. It's going to take 1 session, maybe an hour and a half, for students to have a really good hypothetico-deductive teaching session. So the efficiency is huge, and unfortunately in higher education, efficiency, cost, time is a driver now, but this is efficient. The cost is vastly lower than using mannequin-based simulation. Advances in virtual patients, and this is one example, a CAE virtual patient, allows us, in fact, in some ways, to better get the message across to our learners, because we can easily see the patient. We can make the patient diverse. We can change their skin tone, pallor, go pale if they should be pale, sweaty, etc. The whole class can see that. They don't need to go up and feel the patient. They can maybe assess the skin using the tools, and it will report it's hot. Sounds are really good. They can be projected to the whole class. Engagement comes in because, as Kat has explained, we ask them, what should we do? What's happening? What do you think you're hearing? What do you think you're seeing? So there is an engagement there. Do they all have to do it? I'd argue no, they don't in early years of undergraduate curriculum. But the final opportunity provided for virtual patients, and this is where I'm talking about coming full circle really to those early slides that Eugene showed of the physiology laboratory, is being able to carry out challenges and, if you like, experiments, such as sending our virtual subject up to the summit of Everest, maybe putting them down depth, underwater, subjecting them to various challenges, or looking at their pathophysiology and exploring what happens if that deteriorates. The advent of virtual patients, where the students can have their own instance of a patient, is actually with us. We don't use that yet, but we hope soon we'll be able to, that all of those learners sitting in that lecture theatre for a few minutes in Teams can assess their own patient, or apply maybe a hypoxic gas mixture, or remove some blood volume, and see what happens to their instance of the patient. That, for me, is really exciting, because we're almost getting back to truly experiential physiological learning. And that's where we're kind of concluding today. I'm going to move on to some thanks, but everything that we've talked about in greater detail in our book. And so if you are interested in learning more about how we do things, please do read our book when it's out, or engage with us and help us to move forward on this journey to teach physiology. Can I have the next slide, please? So just a few thanks, Sim Editor and Sim Zine, who are hosting us today and publishing the work that we've described. And really, the main people to thank are 3 people who have always championed physiology. Simon Walls, who no longer is at CAE, but who put me and Willem together and said, you guys need to write a book. Stefan, who has been with CAE and previously METI, you may know for a long time, the anesthesiologist, chief medical officer, until quite recently, has always championed physiology. And Mandy, who over a number of years has invited these weird physiologists to come to various meetings and talk about the opportunities that simulation might provide. It's a little bit different to what we might normally see in healthcare. So thank you, Mandy, and thank you for hosting this for us. There's a little QR code there. I think it links to the page for the book, which is going to be out very soon. Maybe it works, but you can find it on some Zoom anyway. Thank you.
Okay, well, firstly, a huge thank you to you, Rich, to Kat, to Willem, to Eugene, and hopefully that's really sparked people's interest into how to teach physiology across any professions that use physiology. So we do have some questions have come in. So I'm going to ask the team at Bristol to start off on this first question because it's about you guys, saying, based on your experience as a group, we have a technology lens and we have an educator lens, what barriers have you found when trying to implement this, maybe across the University of Bristol or maybe with other institutions that I know you have presented this? So would love to hear your thoughts.
Shall I start, Rich?
Yeah.
So I guess if I start on locally within the department in which we work, one of the barriers is that a lot of the people that we work with, their research is at the molecular and cellular level, or sometimes organ level, and the number of people with experience of systems physiology, and in particular the interaction and interplay between systems, is becoming less and less within our particular department. And also, I think there's a degree of almost phobia, especially when we had a physical mannequin. What we find is when we get people on board and they come and develop their experience of simulation, that most of them want to do more simulation. And I think it's about doing the spade work for them in terms of giving them the materials that they need to make good, efficient, and effective use of their time. And I guess looking at other schools of physiology, not just in the UK, but all over the world, that now that the simulation uses virtual patients and virtual subjects, I think this is going to be one of the biggest things that makes it much more available in terms of cost, both to other schools across the UK and elsewhere.
I completely agree, Eugene. I would just the cost was a huge barrier. When I used to speak at meetings, physiology departments or biomedical sciences departments would say, hey, it's okay for you guys. You've been able to buy these simulators. That is no longer an obstacle. We're talking about the cost of a simulation, a license being less than some of the other kit, like digitization boxes, of which you have to have multiple numbers in the lab. The second one, of course, is location. And that used to be perceived as an obstacle for colleagues maybe in simulation centres that would say, well, yeah, but we're in this hospital simulation suite. We don't have physiologists, we don't have biomedical scientists or the students. Location is no longer an obstacle. Tetherless mannequins made it easier. Virtual patients make things very easy, much easier. And the final one, there are lots, but the final one I'm going to mention is good scenario design. So we all know, we've all had experiences where we've got some wonderful opportunities, but people don't have the time to develop scenarios, or they're not experts, and there aren't enough cats, there aren't enough Eugenes. Good scenario design allows people to plug in to simulation. If you're running just one session with all of your students, I can always be there, and therefore I can invite a colleague along who might be an expert in that particular area of physiology, or a clinical colleague and you're saying to your clinical colleague, just come along for 2 hours and you can go away again. And that makes a huge difference, knowing that you're teaching with specialists and having accessible scenario design with a good structure. And in the book, we describe what we consider to be the best structure for scenarios for teaching physiology. And that means you can slot into them. You can jump on board if you've got someone like Kat, and off you go. And that's what we really want to achieve.
Thank you. I'm just going to bring in Willem here because you touched on the design and we've had a few comments about that. So Willem, who has taught all over the world and has a wealth of experience along with the team at Bristol, you mentioned in the book about design. Have you informed any of the international national standards of best practices? Because they tend to be written from a very healthcare lens as opposed to a more maybe a scientific. So have you contributed or are aware of any work that could maybe guide people?
The short answer is no, but I can elaborate a little bit. I've been involved in teaching acute care, simulation-based training, mostly in acute care, of course, where these international standards are very important, briefing, debriefing, etc. A long time ago, I was involved in physiology teaching, but then Eugene and Rich went a lot further in that. And as far as I know, we did not refer to the same processes. And I saw there's a question from Lulu from India talking about the debriefing process, and that process is totally different in physiology teaching than it is from training in acute care. So the editor-in-chief, and that will be my closing sentence, editor-in-chief asked us to add a chapter or a section on adult learning theory, which was a very good thing. But in the same time, I think we're setting the learning theory for this type of teaching.
No, I would totally agree. I think a lot of the standards are written from that clinical lens, and I think simulation as a pedagogy, we need to look at different branches. So I think teaching sciences. So I think these debrief models are yet to be invented. But I just want to say it's just after 6 o'clock now. So in the UK, 7 o'clock Central Europe. So that really concludes our webinar this evening. So I just want to say again, a huge thank you to all of you, to you, Rich, Kat, Willem and Eugene, for really painting a wonderful picture. I, for one, will be buying the book for my own students because I really think you're demonstrating how simulation can go not just in the clinical world, but teaching sciences, physiology. So thank you very, very much. And I hopefully everybody on this webinar, please look at all of the work that's coming out about this. And thank you very much. And it's been a real privilege being with you this evening. So I will say goodbye and cheerio.
All right.
Thanks, Mandy.
Thank you.
Bye
Cheerio.
all.
Bye.
Good night.